Welcome everyone, I am López and I will present the work entitled Thermophotovoltaic Efficiency Measurement at High View Factors. I will start with an introduction about how the thermophotovoltaic efficiency is defined, to later explain different experimental techniques that are used to measure this efficiency. Then I will explain how is the new setup that we have implemented to this end. And finally, I will show some results and conclusions. The efficiency of photovoltaic devices has been measured for solar and for TPV applications. However, while for solar applications there is an agreement about how to calibrate these measurements, which facilitate the comparison of results and lead to a faster advance, for TPV applications this is not the case, and different methods are used to estimate the TPV efficiency. This efficiency is defined considering that the power reflected by the cell is not an energy loss. This is only true when there is a high view factor between the emitter and the cell, because then all the power reflected by the cell can be received by the emitter to be recycled. If the emitter is not a perfect black body and the emissivity is less than 1, then multiple reflections can take place. This is what happens in real TPV systems, and this is why we need optical cavities to reproduce the operation conditions. For this reason, the TPV efficiency is not only the efficiency of the cell, but the efficiency of the whole optical cavity, which complicates the measurements. So, although this is what we want to measure, in practice we usually need to place the emitter and the cell at a higher distance for practical reasons. Then the optical cavity is lost because multiple reflections cannot take place, and the TPV efficiency cannot be obtained. Instead, what it is defined as photonic conversion efficiency, which is the efficiency of the cell, is measured. A typical strategy used to convert this photonic conversion efficiency into a TPV efficiency consists on assuming that what we measure is just a portion of an imaginary optical cavity. So the effects of multiple reflections can be included if we define an effective emissivity. This parameter is used to calculate the TPV efficiency together with the external quantum efficiency of the cell, the apparent view factor between the emitter and the cell, and other parameters. However, this strategy has some disadvantages. First of all, some assumptions are needed. For example, it is assumed that the optical properties, which are usually measured under specific solid angle conditions, can be extrapolated to the conditions of real optical cavities. Besides, the results depend on the reproducibility of these optical properties because they are measured at different moments. And low power densities are obtained if low apparent view factors are used. In order to increase the power density, we can increase the apparent view factor if we increase the size of the emitter. However, if the emitter and the cell are placed at a high distance, then we don't have an optical cavity because multiple reflections cannot take place. Using a different strategy, where the view factor is increased by approaching the emitter and the cell, we can obtain a real optical cavity, so the TPV efficiency can be measured without assumptions. This is the approach that we will use in our setup. In this setup, the TPV efficiency will be obtained from two in situ measurements. On one hand, the measurement of the electrical power generated by the cell, and on the other hand, the measurement of the heat flux that is established to keep the temperature of the cell at a constant value. When this is the case and the temperature of the cell is constant, there is an energy balance, so all the power absorbed by the cell is transformed into electricity or into heat. This energy balance is what makes possible to obtain the TPV efficiency using in situ measurements. This is a sketch of our setup. The distance between the TPV cell and the meter is small enough to provide high view factors in between 0.91 and 0.98. Under these circumstances, it is possible to contact the cell if we use the same structure to contain the meter and the contact proofs. So, if the meter is well isolated from the structure where it is contained, then it is possible to heat up this emitter with the light of a high-power laser, while the proofs are maintained at the same temperature than the cell. To this end, all the perimeter is refrigerated with different coolers. The temperature of the cell is kept at room temperature using a Peltier module that forces a heat flux through a structure that is used as a calorimeter. These are pictures of the main parts of the implemented setup. This is a picture taken from above, and this is a picture taken from below. Here you can see how the graphite emitter is contained in this structure. So this part, this surface of the emitter, is the one that will face the TPV cell, which is placed here below. You can also see the proofs that are used to contact the TPV cell, some thermocouples that are used to measure the temperature in different places, PT100 that are used to measure the temperature in the structure that act as a calorimeter, different coolers that surround this structure to refrigerate it and therefore refrigerate the contact proofs, and a Peltier module that refrigerates the TPV cell. So, during the measurements, the temperature of the cell and the temperature of the contact proofs are controlled to be equal to the room temperature. This is just a picture to illustrate how the TPV cell is aligned respect to the contact proofs. So, once this alignment is done, the TPV cell can approach the emitter to obtain high view factors up to 0.98. All these elements are placed inside this vacuum chamber, where the light of a high-power laser is introduced to heat up the emitter. The temperature obtained as a result is measured by this pyrometer. In this experimental setup, the experimental uncertainties are dominated by the heat flux parameter, but they are low enough to provide an efficiency uncertainty less than 2%, which is quite acceptable. Here we saw some TPV efficiency results obtained for different emitter temperatures. The blue points correspond to measurements obtained with our setup, where indium gallium arsenide cells with back reflectors provided by Antora Energy have been tested. These results are compared to the record efficiencies reported in the literature that are represented by the red points. Let me point out that these record efficiencies were obtained using high emitter-to-cell distance. So, different assumptions and non-in situ measurements were used to it. In this other graph, the power density is represented in the y-axis. As you can see, if we extrapolate the results to higher temperatures, similar to the ones used in the literature, then higher power densities could be obtained with our setup. This is a consequence of using high view factors, and it is important because issues related with series resistance will only be visible if the TPV efficiency is measured when high power densities are generated. So, in conclusion, a setup to measure TPV efficiency close to real system conditions has been implemented using an optical cavity with high view factors. TPV efficiency uncertainties less than 2% has been obtained from in situ measurable parameters, and high power densities could be obtained in comparison to other experimental techniques, which is important to account for possible series resistance issues. This is all. Thanks for your attention, and I will be happy to take your questions.